Let's talk about Chapter 24, processes used to fabricate metallic materials. First, we'll talk about the welding processes, and then we'll talk about the brazing and soldering processes. The difference between welding and brazing is that welding is going to melt the base material, whereas soldering and brazing do not. The filler metal in soldering and brazing acts more like a glue. The difference between soldering and brazing is just a temperature distinction, 840 degrees. Anything less is soldering, anything greater is brazing. Welding has been around a long time. The first really practical welding setup was acetylene and oxygen. This gets up to about 6,000 degrees and is plenty hot to melt steel. The flame of the oxygen and acetylene is set in such a way that it's 50% oxygen and 50% acetylene. What this does is creates a very hot flame, but also an inert atmosphere where more excess oxygen cannot get to the metal as it's melted. This results in clean welds without having to use a flux. Gas welding is very slow. It's not used often for production situations. It's used occasionally for field work where you can't get a generator or electricity. Gas welding is a very self-contained setup. All you need is the tanks, the regulator, the hoses, the torch, and you're good to go. Gas welding can be performed without a filler metal. This is called autogenous welding. Sometimes this is used for thin sheet metal and certain kinds of joints. But for the most part, filler metal is going to be used. It's worth noting that oxyacetylene rigs can be used for cutting steel as well, and they can be used for brazing. So there's a difference between braze welding, brazing, and gas welding. Here we have our oxyacetylene torches. These have been around since the beginning of time. They're a little slower than the arc welding processes, but you don't need electricity. All you need are these two tanks, regulators, the hoses, and a torch or welding tips. This is an oxyacetylene torch. This little handle right here is to introduce more oxygen to the cutting process. So it's got gas and oxygen. The gas is always red, the oxygen is always green. The gas, the red one, will have left-hand threads. So it's basically impossible to install these backwards. To light a torch, we usually start with the acetylene. The oxygen by itself won't light. So we start with a little bit of acetylene, get a nice acetylene flame. You can see all that black smoke. And then we're going to introduce slowly oxygen. A nice acetylene flame. And as we introduce oxygen, the flame will turn blue. We get a pretty decent little flame. What we want generally is a neutral flame. This is pretty close without getting too into it. If we want to do some cutting, we'll adjust this out and it'll add oxygen. There we go. And that'll be perfect for cutting through material. For the welding tips, welding tip looks like this. All you have control over is the amount of oxygen and the amount of acetylene. And this just provides you with a flame to do welding, brazing, etc. Here, I'm just welding some sheet metal with an oxyacetylene torch with a flame that's a little bit too hot. But you can clearly see how slow this process is. This is just thin steel. The thicker steels would take way more effort. So the next big development in welding was stick welding. So shielded metal arc welding. The shielded part comes from the electrode coating. So if you've ever seen an electrode, it'll look something like this, right? If you look on the end, this is where you clamp the electrode holder or the stinger that provides the current. And this is the end that does the welding. So as you weld, this gets eaten up and gets put into the base material. Before they had electrode coverings, before it was shielded metal arc welding, they tried to do this with just bare wires. So underneath the coating is just a bare piece of metal. What happened was, as they were welding along, there was nothing to cover the weld. So you had this very, very hot molten metal with no shielding of any kind. If, as you know, when you put metal in an oven, right, it oxidizes at higher temperatures. So it's sucking up all the stuff from the atmosphere and mixing with the metal. When something is in an oven, it's just the outside surface. You can chip that stuff away or sand it off, no big deal. But when you have molten metal, that stuff is all churning around, right? You're adding metal, the metal that's already there is mixing up, so you're getting those impurities all over the place. What they figured out was that if you just add the coating to the outside of this stuff will burn away and kind of kick the oxygen out of the room, right? It displaces the atmosphere. In the beginning, these were just cellulose. It was basically just wood fibers, just something to catch fire and create smoke and get rid of the atmosphere. So a stick welder has an electro holder, aka stinger, right? These are gonna hold our electrodes, right? The electrode is a bare, it's got a wire in there with a filler metal, and the outside is basically just stuff that burns up and provides a clear atmosphere for your weld. There's all kinds of formulations. This is a 60-10 rod, and we have 70-18. There are two of the more popular ones. So you just place this on the stinger. Just like a MIG machine, you'll ground your workpiece, and as you weld, this will get eaten up into the weld. This might be good for a 8-inch weld. It's a 14-inch rod. Because once you get about right here, you can't really weld with it anymore. So one downside of the stick welding process is you have to throw this little bit away. So as you weld, you just get comfortable and go along wherever your weld seam is. These are convenient in the field because they make these leads that are 400 feet long, right? So you can be on one end of a ship, plug in your ground clamp to one end of some huge metal structure and be 400 feet away welding with this. Whereas the MIG welder, you gotta keep those gas tanks with you. So it limits the length of the leads, right? Stick welding is great for the outdoors because as this stuff burns up, it provides its own atmosphere. Wind won't really affect it, whereas wind will blow away the shielding gas from MIG welding and TIG welding. Here's a quick demonstration of stick welding. Strike the arc, sped it up to move along the weld, and at the end it has to be chipped, the slag has to be chipped away to get to the actual weld. Let's talk about the next evolution in welding technology. So we discussed a little bit about how irritating it is to change out sticks every time you reach the end of an electrode. What MIG welding does is instead of using individual electrodes, you have a big spool of wire. So the spool of wire does two things. It provides metal for the arc and it provides filler metal. But this wire in typical MIG welding is bare. So it has to be protected from the atmosphere. The way this is done is with shielding gas. So this is argon, helium, or carbon dioxide. The MIG welding process is 2 to 3 times more productive than stick welding. It's certainly the most popular for indoor production settings. It's very easy to learn. It's relatively easy to automate. So to have machines or even simple things with like a positioner and somebody just pulling the trigger, it's a very simple system. It leaves a clean weld with no slag. So there's no need to get a chipping hammer and a wire wheel to clean up the weld. This makes subsequent welds even faster. So sometimes you have to put 3 beads on a weld to get the right thickness, the right depth. MIG welding is very, very fast with this. MIG welding can be a little bit more difficult to use in remote locations because of the setup where you have to run the wire, the shielding gas, and the electricity through the cables. So those cables typically don't come in extremely long lengths like stick welding. Stick welding, you can have a 200-foot cable, no big deal. MIG welding, they're typically like 10 feet long. Maybe you could get 20 or 30. In addition to the cables, you have to get the tanks somewhat nearby. In addition to that, you have to worry about the shielding gas. A strong wind will blow the shielding gas right out of that weld and will expose the hot metal to oxygen, which will ruin the weld. MIG welding is best used indoors. There's another variety of MIG welding called flux core arc welding, FCAW. This uses the standard MIG machine, but inside of that bare wire is flux. So this acts kind of like a cross between the stick welding and the MIG welding. The flux core MIG welding lets you weld outside much better and is popular for structural items. It makes a deeper, more solid weld than regular MIG welding with a bare wire. We have a MIG welder. This is a little Miller unit made to run on 110 and 220. This is a little smaller than you might see in a production shop, but it still welds. The components of a MIG welder are the gun. This has the wire coming out of it. You can see it moving very, very slowly. Pressing the trigger does 2 things. It starts the wire moving and it starts the shielding gas. You can hear it. You want to make sure your shielding gas is on before you start welding, or your weld quality will be just horrendous. You'll literally see the bubbles in there, so you'll know if it's happening. This is our gas. For steel MIG welding, we typically use 75% argon, 25% CO2. It's got a regulator on it. One side of the regulator lets you know what's in the tank. The other side lets you know what's going to the gun. On the inside of the welder, we have a wire spool. There's a little unit in there that's used to push the wire out to the gun. The last thing to mention is before you start welding, you need to have a ground clamp either to your workpiece or to something that conducts electricity to your workpiece. The closer you can get your ground clamp, the better. You want that electricity to go as short a distance as possible to get to your workpiece. Here's a demonstration of MIG welding on mild steel plate. I sped up the middle portion to save a little time. It gets repetitive. TIG welding was developed in the 1940s to weld aluminum for airplanes. It used to be called HeliArc because it used helium. The technical designation is GTAW, gas tungsten arc welding. So TIG welding operates a lot like gas welding. You have a torch that provides your heat, in this case an electric arc, and you have your filler metal which you manually feed into the weld pool. TIG, instead of using the electrode and the filler metal in the same item, TIG uses a non-consumable tungsten electrode. So this does not get put into the weld pool. It just provides a place for the arc to come from. So the operator has to keep the electrode a very specific distance away from the weld. The filler metal is fed into the weld pool as the electrode melts the base metal, and then it just moves along very, very slowly. This process produces the best welds because the welder has the most control over the weld pool and the filler metal. It provides the most focused heat for all the manual processes. TIG welding can be adapted for just about any metal. So it's used for titanium, copper, aluminum, steel, stainless steel, exotic alloys. Just about anything that can be welded can be done with TIG. So it's a very versatile process. It's the slowest process and it requires the most operator skill. So it's typically only used indoors and in production settings where no other process could do the same kind of precision work. Water-cooled TIG torch, there's a bunch of things that go in here. The red and the black are going to be the electricity. The blue is going to be a little water line. So you want to try not to step over these or drive over forklifts or pallet jacks, right? These are very sensitive. In the TIG torch, we have a cup we have a cup that's a ceramic. On the inside, we have a tungsten electrode, right? These come square and then you sharpen down the ends with a grinder or with a chemical solution, which I'll try to do a video about someday. Inside of this, we have some other stuff. I'm not really that worried about it right now. The TIG electrode is not consumable, right? So in a perfect world, it lasts basically forever. It doesn't get put into the weld as filler metal. They do get screwed up. They get little bits of weld spatter on them and you dip it in the weld, it messes up, you gotta re-grind it. But it doesn't get eaten up like an electrode does. The other side of the TIG welding process is your filler metal. You'll hold this by hand. So you'll use this to heat up a little area on the metal, make a molten pool, if you will, and you'll dip the rod in there and then you'll move to the next spot. So it's a very slow process, but very precise. You can really put that heat in a very small, directed area. TIG machines use shielding gas as well. If you can see back here, we have our shielding gas. Typically for regular steel, we'll use 100% argon. This thing is great for carbon steel, aluminum, and stainless steel. With this setup right here, we can switch from AC, the little squiggly waveform, to DC pos and DC neg and do a lot of different cool. Here's a demonstration of the TIG process. The middle part is sped up 1,000 times. This is a very slow process. So out of the TIG welding process came what's called plasma arc welding, or PAW. Plasma arc welding is a more expensive, more complex process that you won't see in a lot of shops. What it does is uses the same kind of tungsten concept as TIG welding, but it's going to force plasma, which is just a regular shielding gas or hydrogen, at high pressure through the nozzle. As the plasma gas hits the arc from the electrode, it's going to create a ton of heat. This heat is used to melt the base metal or to cut. So this is how plasma cutting works. The big difference is that between plasma arc welding and TIG welding is that the electrode is recessed in the nozzle to constrict the arc. The plasma gas isn't quite enough to shield the metal, so it's got to have a separate system of shielding gas and an outer nozzle. One of the benefits of the recessed nozzle is that you have less contamination of the electrode. So it requires a little bit less maintenance on a weld bead to weld bead basis. These are popular for stainless steel, pressure vessels, things that need deep, narrow, precise welds, and they're usually going to be automated. Resistance welding, it's often called spot welding. So what this does is puts two electrodes on either side of usually two thin pieces of metal and has the arc go between one electrode and the other through the material. This creates heat and temporarily creates a molten state where the materials will join. It's really only useful for thin things, and it's often used to replace mechanical fasteners like rivets. It can be done relatively fast and is popular for all kinds of sheet metal applications. Seam welding is a variation of resistance welding. It uses the same principle. 2 electrodes, the electricity goes, the arc goes through the material, creates heat. Seam welding, instead of being in one spot, is going to be along a length. The typical way it's done is having a wheel that's the electrode, and then something below it. The wheel moves and it's creating a little spot of molten material as it moves along. So at the beginning, you have one spot. At the end, you'll have a whole seam. Inertia welding is highly automated, very good for mass production. What it does is forgoes using the gas or the electric arc and just uses friction to create a weld. So the way it typically works is you'll have something like a lathe, you'll have something stationary, and then a part spinning. You'll put the part spinning onto the stationary part, and it'll develop friction at that interface. The friction develops heat, and at some point it will be hot enough to where when the machine stops, the 2 parts will be permanently joined together. It's a good replacement for some upset forging processes where a lot of straightening has to occur. Inertia welding produces very strong welds and can save money in certain applications. Electron beam and laser welding are very similar in that they don't have to contact the workpiece. They also produce very deep and narrow welds. This can save money in things that are plate that's, a couple inches thick, because in a typical stick, MIG, flux core process, you end up having to make a bevel and a V and fill the whole thing up with weld metal. With the electron beam, you eliminate all that extra weld metal and all the extra heat distortion that's involved. So both of these processes, the beam is so focused, you get very little heat distortion. So they're good for both small, accurate workpieces and large things that have to hold tight tolerances. The electron beam works by shooting electrons at the weld area, whereas the laser uses a laser, right? Both of them need some kind of shielding, so they're usually done in an argon chamber that's totally evacuated of oxygen and atmosphere. Both of them are largely automated. That's almost all done with computers. You would have an operator, program it and press start and stop, but you would never have an operator, running a joystick or something to actually make a laser or electron beam weld. Soldering and brazing are used for many applications, typically for non-ferrous metals. They're used in situations where you want to minimize heat distortion. Because you don't melt the base metal, you apply a lot less heat to the joint. They both work by capillary action, where the design of the joint causes the metal to go into the joint. The process involves heating the metal with a torch or induction, and then you add the filler metal to a fluxed area, and the filler metal should, just go into the joint and create a good seal. This is how copper pipes are brazed together. The difference between soldering and brazing is the filler metal and the temperature. So anything less than 840 degrees is soldering, which is typically lead or tin or any of the replacements for lead. Anything above 840 is considered brazing and typically use copper, bronze alloys, or silver. Silver can be used for just about anything. It's very strong and electrically conductive. However, it is expensive. There's hundreds of brazing alloys out there as well as soldering alloys. So if you have to braze something, you want to find out exactly what you need. With soldering and brazing, the surface preparation is particularly important and the flux is important. So the surface has to be clean, free of dirt and oil, and the correct flux has to be applied. The flux acts like the shielding gas or the electrode coating on arc welding. Protects the filler metal while it's very, very hot. and it aids in the capillary action. Both soldering and brazing require very close fit up, whereas some arc welding processes don't require a great fit up. Usually gaps of 5–10 thou for most soldering and brazing is acceptable.